genes, modifying existing ones, or removing competing pathways, metabolic engineering aims to create microorganisms that efficiently convert renewable raw materials into valuable chemicals, fuels, or other products. This approach helps in creating a more sustainable process by minimizing waste and emissions. So, sa study, metabolic engineering is important in the bio-based production of alkanes and alkenes. Hydrocarbon typically derived from fossil fuels. The research demonstrates how engineered microorganisms can be optimized to increase the efficiency and yield of these hydrocarbons from renewable resources. Alkanes and alkenes, fundamental to the chemical industry, are targeted due to their importance as fuels and raw materials by developing microbial systems to produce these compounds sustainably. This study aims to provide an eco-friendly alternative to traditional petroleum-based processes, contributing to a more sustainable and circular economy.
The study utilizes Escherichia coli, E. coli or Saccharomyces cerevisiae, both commonly employed in metabolic engineering for bio-based productions, while specific microorganism used is not mentioned. These organisms are prominent choice due to their extensive use in biotechnology. E. coli, a gram-negative bacterium found in the intestines of warm-blooded animals, is favored for its well-characterized genetics, rapid growth, and ability to express foreign genes. It can be genetically engineered to produce various chemicals, including alkynes and alkanes, by optimizing metabolic pathways to convert simple substrates like glucose into hydrocarbons. Saccharomyces cerevisiae is a eukaryotic yeast species. Is also popular choice for bio-based productions. I know for its use in baking, brewing, and bioethanol productions. Cerevisiae has a more complex cellular structure compared to E. coli. It is well characterized and adaptable to industrial conditions, making it suitable for producing biofuel and chemicals by introducing pathways from other organisms or optimizing its native networks. Cerevisiae can be engineered to produce alkenes and alkanes from renewable feedstocks like sugar. Both microorganisms are ideal for sustainable biofuel production due to their rapid growth, scalability, and ability to convert biomass-derived sugars into variable hydrocarbons.
The study focuses on developing metabolic pathways in microorganisms for efficient production of alkanes and alkanes. Essential hydrocarbons derived from petroleum, E. coli, and S. cerevisiae are commonly used in metabolic engineering due to their suitability for hydrocarbons production. The pathways are manipulated through fatty acid synthesis, decarboxylation, and decarbonylation pathways. Genetic modifications such as overexpression of K enzymes, knockout of competing pathways, introduction to heterologous pathways, and optimization of regulatory elements contribute to sustainable production and reduce environmental impact.
Successful experiments require proper setup, including selecting the right equipment, materials, and microorganisms. It's also crucial to control environmental factors such as temperature, pH, and nutrients levels. In metabolic engineering, we focus on optimizing microbial strength, enhancing microorganisms for better product yield. Genetic modification engineering microbes to reduce the necessary enzymes. And lastly, culture conditions and adjusting conditions in bioreactors for optional production. Essential steps include designing or identifying pathways, establishing the metabolic pathways for alkanes and alkenes, genetic motivation, altering microorganism to enhance enzyme experience, optimizing metabolic flux, improving the flow of metabolites, improving strengths, using techniques like mutagenesis to enhance strengths, scaling up in bioreactors and developing methods for product extraction, isolating alkanes and alkenes efficiently, product characterization, ensuring quality and effective production of alkanes and alkenes involve careful setup, optimization, and scaling. Efficient product handling is key to success.
Results, studies, findings, and data on alkenes and alkanes production. Recently, studies have shown significant advancement in the microbial production of alkanes and alkenes. For instance, research utilizing engineered E. coli and Escherichia strains has demonstrated the successful incorporation of synthetic pathways. Then galid ni siya sa high yields productions of alkenes like ethylene and propylene. And sa alkane sad na ay hexane and heptane. The data indicated that these engineered microorganisms achieve enhanced production rates and specific yields compared sa natural raw or less optimized nga strain. With advancement sa enzyme activities and metabolic flux is contribute siya og improvements. Result: comparison of production levels before and after metabolic engineering. Before metabolic engineering, our microbial strains typically produced low levels of alkanes and alkenes, often in the range of milligram per liter. Then after ga-implement sila og genetic modifications and optimizing metabolic pathways is ang production ga-increase significantly. For example, engineered strains can now produce alkanes and alkenes at concentrations of several grams per liter, representing an order of magnitude increase in productivity. These substantials improves highlights nga effective gyud ay ang metabolic engineering sa pag-enhance ng efficiency of the yield and sa bio-based production processes.
Conclusion, the summary of key findings and contribution. So the study highlights significance, progress, and bio-based production of alkenes and alkanes through metabolic engineering. Key findings include the successful implementation of synthetic pathway and microorganisms like E. coli and Escherichia, leading to dramatically increased production levels of this compound. The researchers demonstrate that genetic modification of optimizations of metabolic pathways can enhance yield by order of magnitude compared to unmodified strain. So this contribute to the broader fields of metabolic engineering by improving microbial production. So the importance of bio-based production in sustainable agriculture is underscored by its potential to reduce resilience on fossil fuel and lower greenhouse gas emission. By producing
alkenes and alkenes through engineered microorganisms. The study support the development of renewable alternatives to petrochemicals products, contributing to environmental sustainability. This approach aligns with the goals of sustainable agriculture by promoting the use of biological process and resource in place of non-renewable ones, thereby fostering a more eco-friendly and resilient agricultural system.